Hello, students. So this is part 2 of Lab 8's tutorial. And so in this part of the lab, we're going to basically learn how to import our DEMs that we downloaded from the Utah Geographic Referencing Center into ArcGIS Pro. And we have two, so we're going to basically mosaic them into one data set. I'll show you how to clip it to your area of interest in one way. There's many ways you could do this. And this is a quick and dirty one. So it will be reasonably easy, and everybody might get a slightly different result, but that's okay. And then from that clip DEM, we're going to make a bunch of derivative products that we can use to visualize the landscape, including hillshade map, aspect map, and slope map. And I might talk about a couple of others as well. Okay, so hopefully you are seeing my screen, and I've got Lab 8's kind of directions up here. We're done step 1, so we'll move down to step 2. And here it says to extract the DEM and open it in QGIS. You don't have to use QGIS. I'm actually meant to say ArcGIS Pro. Last year I required students to use QGIS a little bit, but probably better, since we haven't done this before, to do it in ArcGIS Pro and go from there. Okay, so over on the right, you can see my catalog pane, and I've got two folders connected. One is this APRX project folder, which includes like the geodatabase that was automatically generated and the toolbox for this ArcGIS Pro project. But I also have a folder where I've downloaded the data that I collected. So that includes Landsat data from June 2022 and 2023, and a 10-meter digital elevation model for the San Rafael Swell. And so I have these two already extracted files. Note that I've already basically gone in and extracted the Landsat data as well. Every GIS file that you're going to download pretty much is going to come as a zip file. So first thing you want to do is organize it into the folder that you want to save it in a well-named folder, so you know what's going on, and then extract those files there. Here in catalog, we'll see them as one file, but they're always multiple files, which is why they tend to be zipped up instead of just downloading one at a time, because that could risk corruption. Okay, so I am going to, I've gone over here to the left in my map and actually made what are called group layers. And so I've organized my files into group layers. So if I want, I can add data directly to the appropriate group layer. I believe I can also drag it into that group layer, and that's what I'm going to do here. So I'm going to drag both of these into the DEMs group layer. There comes the first one, and here's the second one. And so you can see that it's a pretty big two sets of tiles. These are 10-meter tiles. We range in meters from 1,234 meters above geoid to 3,101 meters above geoid. I believe these are in UTM NAD 83, which is going to be important when we do our math and derivative products of slope, because those rely on trigonometry. So let's just check that. So the source map, or the source information, if we go to the spatial reference, yeah, we can see it's UTM, and the linear units are in meters, not degrees. So that's good news, because we're going to multiply and divide meters by meters. Okay, so the issue that we have right away to solve is that there's a seam here. And so we want it to be seamless, and we want to basically image this, this feature that we can see right here. This is the San Rafael Swell. Basically, it's a monocline, so all the rocks right along here are folded up and over here. There's like a hole in here, basically, where weak rocks have been eroded and spit out into the Colorado Plateau. Out here, the layers are pretty flat lying, generally dipping back this way, folded up and over right through here. And so that's what we want to look at. So, see, I've zoomed into the kind of the area of interest for me. And so what I'm going to do is this, I'll center it a little bit more. It's not perfectly centered, of course, because, we don't have these tiles over here. But this is pretty much what I want to do and work in. So we're going to use that screen basically to operate on this next step. Okay, so how do we combine these together is called mosaic to new raster. So we can click on the geoprocessing tools here. We can go to analysis and click on the tools there. There's a bunch of different ways to pull this up. But I'm going to say mosaic. And then I can see the second one here is mosaic to new raster. And I can click right on that and get started. But if I pull over to the side here, you can see data management tools comes a link. I like to click on that, especially when I was a student learning, and I suggest you do too. Don't speed through this, but click on this. And what it does is it pulls up where in the toolbox this tool lies. So you can see that it lies under data management tools. And under that, there's a raster toolbox. And this is under something called raster dataset and mosaic to new raster. And so you can see there's some other related functions like copy a raster, create a random raster, generally mosaic. So that's not to a new raster, but linked rasters. So that's another way to go without making giant files. Anyways, these are related tools. And so you might find in the future that you want to do something that you don't know what it's called, but you know that you can mosaic to new raster. So you might find your way to this part of the toolbox system and see what else is available. Raster processing might have some, clip raster. That could be useful. And so, yeah, so it's a good idea to familiarize yourself with the toolbox because you don't always know what you're looking for. Don't just go search and then use it all the time. Okay, so let's mosaic to new raster. Okay, so then we can use a drop-down menu to select the DEMs that we want to. If you're like, wow, you've got too many files open, kind of like I do here, and you could get confused, you can also go to the folder that you downloaded them from and select them that way. But I can see them here. They're under DEMs, and it's this one and this other one. Okay, and then I'm going to save these. Actually, what I'm not going to do, because I might want to use QGIS in the future to profile through this data. So I'm actually going to go back to my folders. I'm going to put it in Lab8 in that DEM data. And that's going to be my folder, 10-meter DEM folder. You could put it in the geodatabase. But one thing that I have noticed is sometimes it doesn't like to accept my GeoTIFF file extension in the geodatabases for all tools. I think it would for this particular tool. But the other problem is that if you want to port to another program such as QGIS, it doesn't read ArcGIS geodatabases easily. So this will just make my life easier for portability to save it to this other folder. So I'm going to call this San Rafael DEM 10M, 10 meter, dot TIFF. Okay. So we can see what dot extensions are possible. No extension, if you don't give any extension, it'll produce an Esri grid file. And that is, if you get errors when you're saving to your geodatabase, you might just give it no extension. And usually that solves a problem. But there are some limitations of certain file types. So like in the case of Esri grid, I think there's a limitation on the number of characters in the name, which could also give you an error. And so knowing about kind of some of these program limitations can help you troubleshoot issues you might be getting when saving. When you're saving from our GIS lab, You're often trying to save to our data server on campus, which is a great solution to make sure it's redundant and backed up. But you sometimes will get errors when you're processing DEMs, especially later in this lab when you do ArcHydro tools, and there's a lot of computation going on over the network. If there's any hiccups in that network connection, you can actually corrupt the data that's being saved and it will fail. And so sometimes you may also need to save to a local folder as you're doing some of these intensive processes. And then at the end of the day, back up your data to that file server. So if you're getting an error, don't say, oh, this program is just not going to work. You have to find a workaround. And sometimes it's changing the file extension. Sometimes it's shortening the name. Sometimes it's changing where you're saving to because of a network issue that day. Yeah, we always have to troubleshoot when doing GIS work. Okay. So the spatial reference, I'll just copy from one of the input data sets. By the way, if you didn't choose that, that's what it would choose to do, but I like to make it certain. Pixel type is really important. This is basically like when you're working in attribute table, you have to choose what type of data you're going to save in your attribute table. Is it going to be text? Is it going to be integers? In this case, it's elevation data, and we have details of decimal places. So we need it to be the type that is a float. And the only float option we have here is 32-bit float. So that's what we got to use. And our cell size, we don't have to change this, but I said it was 10 meters, so I'm going to make it be 10 meters. And then when you're processing a raster, it needs to know how many attributes are stored in that raster, or bands. In this case, we call it for raster. This is just elevation, so that's one band. But if we had red, green, blue for color photo, that would be 3 bands. In this case, it's just elevation, 1 band. Okay, so now my trick to clip these 2 data sets to this view is very simple. So go to environments of your processing, and this is something you can find in most of the tools that you use in geoprocessing. And we go to the processing extent. You can limit it to a bunch of different things, same as a certain layer. But what I want to do is to limit it to the current display extent. And so then it cuts it to this box, basically. It'll also be limited by the edges of the data sets, although it may produce no data over there. Let's see what happens. Oh, yeah, no, it says no data, nothing will happen. Okay. Okay, so now we can run this. So I'll say one thing, the reason to process it to a smaller area is the hydro tools that we'll do in the following step or two is kind of fairly intensive. And so having a smaller data set will help us speed things along a little bit. I'm a little worried that it's taking some time to process. But here it came, fine. And you can see if we zoom out where it sits, so I can turn off these other 2, and it popped out to the general map. It didn't put it inside DEM, so I'm going to do that. Okay, so there is my clipped data set. You can see it's smaller than the other 2. So I'm going to minimize those. I could also remove them now. So that's our nice seamless data set showing the elevation of the San Rafael swell. Okay, so that's part 1 of this part of the lab. The next part, we need to create these 3 maps: aspect, hillshade, and slope. And then you're going to make a shaded color relief map here. Okay, it says explore how you can use these overlays to make a color slope shade or color hillshade map which shows relief and elevation. Okay, so we're going to go back to geoprocessing. And I'm going to show you where almost all of these visualization of elevation data tools are. They lie in what's called spatial analyst tools. And so you scroll down within there, and it's in surface. And then in here in this surface toolbox, we see aspect, make contours, hillshade, slope, view sheds, etc. So if you want to operate on a DEM, the surface toolbox within spatial analyst tools is really useful. I will say, however, that if we zoom up to the top here, 3D analyst tools also has a lot of the same stuff. So I got to remind myself where it is in here. So if you go to raster, okay, let's go back this way. So if I say slope and I hit enter, we can find where it is. So we click on 3D Analyst Tools. It's under 3D Analyst Tools, raster, surface, and then you see aspect, contour, curvature, hillshade, slope. These are all very useful as well. And so you can process them in either toolbox. They're going to give you similar results. Not sure why they show up in multiple places within ArcGIS. Perhaps there were different programming groups that were responsible for these different things. Also, these are add-on tools, and perhaps, you know, people sell you the 3D analyst tools, which have some functionalities that certain companies need, and then other companies need some other things that are more statistical related, and they get spatial analyst tools, but they also throw in these as well. So it's probably something to do with making money. Okay, so we got to do these three things. So aspect map is the first one. So we click on that tool. We input our new San Rafael DEM 10 meters. And we're going to output a raster somewhere. If I don't do anything, it'll go to my default geodatabase and it'll just say aspect San Ra 1. If you want to give it something more specific, you could say aspect San Rafael swell 10 meter, or just maybe it's not necessary to say that. And that's good. Now, since I'm saving to the geodatabase, I'm going to leave it as an Esri grid, actually, but I'm going to shorten it up because I think I'll get an error if it's longer than 8 characters. So I'm going to get rid of this well. The aspect. Actually, I can make it even shorter by saying asp San Rafael swell. 1, 2, 3. Ooh. Let's just call it aspect SRS. Other option would be to save it to the other folder like I did before, but I'm not going to do that. So I'm going to click run. And I don't have to change the environments this time because it's only going to work on this data set. Okay, so that should run. In the meantime, I'll start pulling up the other tool. And so the next one we want to make is a hillshade map. So I'm going to pull that up. And there comes our aspect map. And so what you get out of aspect is what's called the slope facing direction. And the data comes in degrees, like 0 to 360 degrees. But the default way that it's symbolized is by categories. And well, if the slope is flat, it's gray, north. So that is 0 to 22.5, but also 337.5 to 360 degrees that comes as red, so on and so forth through here. You could symbolize it in other ways, and I do find usefulness in doing stretched aspect maps to display things like channels in LiDAR data at high resolution. But this is probably what we want to do for now. So let's leave that there. I'm going to turn it off. Okay. So this can tell us things about like, oh, where would be a good place to maybe put something to get good solar influx, solar panels, things like that. Of course, you can also turn the solar panels. But it also can tell us things about, oh, why is this surface a different temperature while it's facing a different direction. It's not getting as much solar input, and so that rock might not heat up as much during the day if we're looking at Landsat data, etc. Okay, so hillshade. So every derivative product of our DEM. So I have a category here of derivative products. Okay, so let's move that aspect map down there. Oh, quick, do it. Okay. And then I'll open my derivative products. And I've actually run these previously and minimized them. But the one that we have, I'll leave open. I can turn it on, and then it sits underneath everything else. If I turn off my DEM, we'll see it. But one other thing that you can do when you use these group folders is you can actually turn everything off in the folder at once, like that. So that's one other reason to use these kind of group layers. Sorry, not folders. Okay, so there's my derivative product. Okay, so we'll turn back on my DEMs. Okay, so all of these derivative products have to be made from the input digital elevation model. So we always need the input raster to be that DEM. So I'll make sure to do that here. And then I'm going to output a hillshade. I'll go with what they give me. You can change the azimuthal angle of this artificial sun angle and how high in the sky it sits. But I tend to go with the default unless I have some other reason to. We don't need to implement a Z factor because we have the same units in the horizontal and the Z orientations, which are meters. If we had decimal degrees, then you need to do a Z factor. You'd have to look this up by whatever latitude you were sitting at to make the math work. So if you have a geographical coordinate system digital elevation model, remember that if you're going to make derivative products like a hillshade, you need to use a Z factor and look that up. Okay, but we don't need that, so I'm going to go ahead and run this. And then in the meantime, I'm going to pull up the other tool, and that is slope. Oh, we're still in surface. Okay, hillshade is about to start. Okay, so for this next one, I also have to go back to the input DEM, and I'm going to output degrees, 0 to 90 for slopes. And there's different methods to do this calculation, but I'm going to go with the defaults again. In the meantime, here's our hillshade map. So if we zoom in, we can see these interesting details of the San Rafael swell and these channels and things like that. I will pause a minute on the no, let's go ahead and process it, get it going. And then we're going to pop over to hillshade after it starts working and kind of visualize a little bit what we want this hillshade to look like. So let's run the slope map. Now we'll go into the symbology of the hillshade. And what I wanted to show here is we're using a stretch, but we're not stretching it. We're just going over the whole range of the histogram data. But if we go to standard deviations, we can kind of tune how dark the shadows are and things like this. So the default is 2 standard deviations. Okay, my slope map is done. I'm going to turn it off for a second. And I'm going to click back on my hillshade. Turn off these. Okay, so back in my hillshade, standard deviations, if we change it to 1 standard deviation of the data that it looks through, how does that look? It gets even darker. If we want it to be a little bit more subtle, we can go to 3. Looks more like what we originally had, which was no stretch. So you can choose what you want your landscape to look like, okay? By just changing the stretch. And you could be really informed about this by opening up the histogram, and I don't feel like it's not showing up, so that's confusing. But anyways, yeah, generally your hillshades are displayed using a stretched color scheme, and generally it's just dark to light because it's shading. You generally would not choose a mixture of colors, but you can always play around. But don't generally, for other people's purpose, do something other than shading. Okay, so I'm going to now move this one down to my derivative products, which is going to turn it off. That one's set up. Now I'm going to go to my slope map. Okay, so this is a slope map, and right now it's categorized, and it's getting darker in color by the greater slopes. And so this is one way to display a slope map. It's not the default always. You can do other things, like you can do like blue to red. That would be a slope map. There's all kinds of ways to do it. A lot of people do it by classification. But if you want to make what's called a slope shade map, which is kind of an alternative to a hillshade, which is not directionally biased, we would stretch the slope map. Okay, and then the default when you do a stretch is dark to light colors. But if we want the slopes to be shaded darkly, then we need to invert this. So we click invert. And now we have something that looks a little similar to that hillshade map, but it is definitely different. I also like to go with standard deviations on my stretch for this slope shade map, because then again, we can tune what we're looking at. So like, for instance, I'm going to zoom in to this kind of flatter area here, just off of the San Rafael swell, and I can't see too much here at the moment. If we go, instead of 2 standard deviations, I go to 1 and see how that changes things. So I think that tunes it to like the more small scale slope differences, so you can see some more of the details in the flatlands. So if you're working in flatlands, you'll tune that standard deviation down to focus more on the majority of the data rather than the high slope endpoints. If you want to maybe not have the San Rafael swell look so dark in color, we can instead go the other way, go to 3 standard deviations, and then we can see more of the details of the topography in the swell itself. Okay, so yeah, that's a slope shade map. So I'm going to also put that down in my derivative products. And then one other thing I'm going to do is move my derivative products above my DEMs. Okay. So now my DEM is on, but I kind of minimized it. Okay. Okay, so let's turn back on my derivative products. And how do we make this shaded relief map? And furthermore, color shaded relief map. So let's go down to the DEM, turn off the derivative products. Here's my DEM. We can make this DEM color coded. And what that means is we'll have each elevation will have like different colors. So it's kind of like a contour map of colors. So we go into the symbology, and you could choose something like this if you wanted. And so low elevations are purple, so on and so forth. High elevations are red. So you can identify areas of like elevation really well by using multiple colors. This is kind of funky. If you want a more naturalistic color scheme, I would go down to like this region of kind of greens and browns and whites, etc. And if you want something with a lot of changes in color, you could go with this one. Boom, it shows you lots of details in the landscape. Again, we can use standard deviations to kind of tune this. So if you want it to, again, focus on the majority of the information, then we would go with 1 standard deviation. But that kind of washes things out. If If you want it to cover most everything across the map with a lot of variations and details, you go to higher standard deviations. If I get a 4, then I really stretch things out across the range and we see lots of great detail. You can see river networks, you can see the swell. It's quite a visual product on its own as a color DEM. If you don't like having so many colors, you can also choose something else. Like you can see these green to browns here. And this is probably opposite relationship because the Colorado Plateau here in this high desert, the lowlands should be brown and the uplands might be more green. So we could invert this. And this might look somewhat realistic to you. Maybe it looks even better if we go back to 2 standard deviations. Or maybe that's too much and we go to 3. Okay, so kind of like that. Okay, so that's the color. Okay, so then what we want to do is turn back on our derivative products, but we're going to turn off the ones we're not using. So I'll start with a slope shade over the top of it. What we're going to do is we're going to go to click on slope and then raster appearance. We can make a transparency here so we can see through the slope a little bit, say like 35%. And so then you see the colors starting to show up through the data. If you wanted to show up more, you can make it like a 50%. If you feel like that's not colorful enough, you could always go back to the symbology of your San Rafael Swell DEM, and you could change it back to this more wild one. And maybe that looks a little more interesting to you. But you can see the relief and the color quite well in this transparency. And so, yeah, this would be called kind of a color shaded relief map, but using a slope map or a slope shade map. Now let's see and compare that. It's not really truly shaded relief, it's color slope shade. So let's go to a more traditional shaded relief, which would be this one with a transparency. So if we made this hillshade 50% transparent. Oh, I did not do that right. So I somehow transparency the DEM. So go back to 0, click on the hillshade, and then go to 50%. There we go. And so I think this will probably look to your eye much more like a natural landscape. Look, you can see really cool things like this kind of escarpment running off across here, intersecting the San Rafael Swell. You can see another kind of fault or fractures and a series of them running off. You got plateaus. This is like a really classic map that somebody might produce to visualize the landscape. And you can make these in a custom sense for wherever you're studying. It's a great overview map. I would say it's much better than the background maps that we have, right? Showing up here. It's much more detailed. Okay, so that is your shaded relief map. So you can choose whatever you like for your final version of this. You can do a screen cap. I'm not asking you to make a layout view for this and just paste it in here. I want to see that you're able to get this to successfully work. If you have any issues, call me over as you're working on the lab. Okay, so that is this part 2. So I'm going to stop the recording.